What if the cheapest place to run AI isn't in a desert somewhere with cheap land and cheap power? What if it's in orbit? That's not a thought experiment anymore. It's a business plan. Earlier this year, Elon Musk stood at the World Economic Forum in Davos and said the lowest cost place to put AI will be in space. And he put a timeline on it. 2 years, maybe 3. Then SpaceX filed paperwork with the FCC for an orbital data center constellation, not a few satellites. To 1 million of them, in low Earth orbit, somewhere between 500 and 2,000 kilometers above the surface. That is an enormous number, and it raises an obvious question. Why would anyone do this? So let's actually work through it. Start with the physics, because that's where the honest case begins. Data centers on Earth have a cooling problem, a serious one. A single modern AI chip can pull over 700 watts of power. Stack thousands of those in a rack, pack racks into a building, and you're generating heat on an industrial scale. On the ground, you fight that heat with water, with air, with massive cooling infrastructure that costs money and consumes more energy on top of what the chips already use. In space, you don't cool things the same way. You radiate heat. Point a panel at the cold of deep space, and heat flows away passively. No pumps, no chillers, no water towers. The vacuum of space is actually a pretty good place to dump thermal energy. And for AI workloads, where heat is the constant enemy, that matters a lot. Then there's solar power. In low Earth orbit, you're getting sunlight about 90% of the time. No weather, no clouds, no night for most of your orbit. Solar panels in space are significantly more efficient than on the ground because there's no atmosphere eating into the incoming energy. You generate power, you use it to run chips, you radiate the heat. The loop is cleaner than anything you can build on Earth. So on paper, the physics actually holds up. The real question is whether the economics can follow. Right now, launching mass to orbit is expensive. Even with reusable rockets, you're still paying a lot per kilogram to get hardware up there. Data center hardware is heavy. Servers, power systems, thermal radiators, structure. Getting all of that into orbit costs real money, and once it's up there, you can't just swap out a failed drive like you can in a building in Virginia. But the cost-to-orbit equation has been changing fast. SpaceX's Starship is designed to bring that cost down dramatically. If you can launch cargo to orbit for a fraction of what it cost even 5 years ago, the math starts to shift. And if you're launching 1 million satellites, you're spreading your fixed development costs across an enormous fleet. That's the bet SpaceX is making. There's also a latency question worth addressing. If your data center is in orbit, how fast can you talk to it? Low Earth orbit is close enough that the round-trip signal delay is relatively small. We're talking somewhere around 20 to 40 milliseconds for a satellite at the lower end of that altitude range. That's actually competitive with some ground-based cloud regions that are geographically far from the user. It's not perfect, but it's not disqualifying either, especially for AI workloads that don't need real-time back and forth. And there's a use case where latency almost doesn't matter. Training. When you're training a large AI model, you're not streaming results to a user in real time. You're crunching through enormous datasets over days or weeks. If your orbital cluster can do that compute cheaply, the slight delay in sending the data up and getting results back is a minor inconvenience. The economics might more than compensate. Now let's be honest about what's still hard. Reliability is a genuine concern. Satellites get hit by radiation. Components degrade faster in the space environment than on the ground. You can't send a technician up to fix a drive or reseat a cable. The systems have to be designed from the start to fail gracefully, to self-diagnose, and to keep running even as individual components die. That's not impossible, but it's a harder engineering problem than running a data center on the ground. There's also the debris issue. We're already worried about congestion in low Earth orbit. Adding hundreds of thousands of large satellite platforms to that environment raises real questions about collision risk, about what happens when old units need to be deorbited, and about international coordination. 1 million satellites is not a small footprint. Regulators and other space operators are going to have thoughts about that, and we should talk about who actually benefits here. AI compute is currently dominated by a handful of massive players. If orbital data centers require the kind of launch infrastructure that only one company in the world currently operates at scale, that's not exactly a competitive marketplace. It's worth watching who controls the orbital computing layer as this develops. Let's step back from the skepticism for a moment. 5 years ago, reusable orbital rockets were still a novelty. 10 years ago, most people would have called a global broadband constellation from a private company science fiction. Both of those things happened. The technology trajectory in this space is genuinely fast. The core idea here isn't crazy. Space has real physical advantages for high-density compute. Cooling is easier. Continuous solar power is available. The chips don't care whether they're above the atmosphere or below it. What has to happen is the launch economics catching up to the vision, and that's been SpaceX's entire project for the last decade. We're probably not 2 years from a functional orbital AI cluster that competes on price with Amazon or Google's ground infrastructure. But we might be closer to a working demonstration than most people expect. And if that demonstration works, the industry has to take it seriously. The lowest cost place to run AI might really end up being a few hundred kilometers straight up. It sounds absurd. It might also be where we're headed.